what is noise? Let's start there. Anybody have any ideas?
Deviation in the signal.
Okay, so deviations in a signal. So that would potentially be the result of noise, but not necessarily noise itself, right? Noise is just an unwanted signal, right? Anything that we don't want, we can classify as noise. So in a circuit, noise limits the minimum signal level that a circuit can process with acceptable quality, right? How many of you have ever heard of something called the signal to noise ratio, right? So if your signal to noise ratio is 1, that means that the power carried by your signal of interest is the same as the power carried by the noise as well. And so it's very, very hard to distinguish between the noise signal and the quantity of interest. If your signal to noise ratio is greater than 1, that typically means that you can see your signal pretty easily as compared to the noise. And if your signal to noise ratio is less than 1, then that means the noise is dominating your signal and what you're trying to do is effectively lost, right? So we'll talk significantly more about signal to noise ratio a little bit later. What we're going to be talking about today is kind of noise as a more generalized concept. So for our purposes, we will consider that noise is a random process. And so what I mean by that is that the value of a noise signal, be it a voltage, current, or whatever, cannot be predicted at any time, even if past values are known. So let's say that we have a simple comparison here, okay? An AC signal generator that outputs some voltage waveform VA of t, and you'll have to pardon my crappy drawing here. A microphone whose job it is to convert the noise of a stream or river into an electrical signal. So for our AC signal generator, this is our time, and this is the quantity VA as a function of time. Our expectation is that we're going to have something like this. And so based on what we observed at some time t1, we can predict what is going to happen at some later time t2, right? So this would be not a random signal. Noise, on the other hand, would look something like this. And we can say that for this particular signal, knowing how it behaved at T1 tells us practically nothing about how it behaves at time T2, okay? So since the instantaneous value of the noise in the time domain is unpredictable, how can we incorporate noise into our circuit analysis, right? So if we observe a noise source for a very long time, we can use the measured results to construct a statistical model, all right? And as it turns out, the overwhelming majority of electrical noise sources obey a Gaussian distribution, which is awfully convenient for us, right? So we could say that probability distribution for most noise voltages, which that's what that Vn is going to represent, should be something like 1 over Vn RMS times the square root of 2 pi multiplied by an exponential function of negative Vn squared divided by twice Vn RMS quantity squared, where Vn is the measured noise voltage and Vn RMS is the standard deviation. Away from the average value, okay? So because the probability distribution function for our noise measurements that we're going to be dealing with in this class are very well characterized, certain properties of the noise signal, like average power, become predictable. So we can't predict the instantaneous value to save our life. But we know that roughly 68% of the time it's going to fall within one standard deviation. What is it, like 32% of the time it's going to fall within roughly 2 standard deviations, and 97% of the time it's going to fall within 3 standard deviations. So we have a very good idea of how things are going to behave. So if we want to figure out what the average power carried by a noise signal is, then we need to refresh ourselves on how average power is computed. So you may recall from circuits 1, actually, taking things old school here, that the average power of a periodic voltage waveform is obtained by taking the integral over exactly 1 period of our periodic voltage waveform squared. So we take the integral of the square of the voltage and then we divide it by the period, and we're normalizing things to some resistor RL. So we're saying the average power absorbed by this resistor RL is this guy here, if we know the periodic voltage waveform, right? This is also how we came up with RMS values and all that kind of other good stuff as well, okay? So what happens if our signal is aperiodic? What do you think we need to do? So what does it mean for a signal to be periodic? After some certain time interval, it repeats. So for a signal to be aperiodic, that means that after an infinitely long time interval, it repeats, right? So we wind up having to take the limit of this guy as our period approaches infinity. So for a random signal, t approaches infinity, which gives us our average signal power is the limit as t approaches infinity of negative t by 2 over positive t by 2 squared divided by RL. And typically speaking, and I know this is going to sound strange, what should the units of this be? Let's start there. Watts, right? So for whatever reason, the resistor is effectively thrown away. And typically speaking, noise power is measured in volts squared. So effectively, all that means is that the resistor value itself doesn't matter, right? So you're normalizing everything to a 1 ohm resistor and then just saying, well, I don't care anymore, all right? So this would be the same, effectively, as the limit for t goes to infinity of the integral from negative t over 2, positive t over 2, just the voltage waveform squared dt. And I'm going to throw a Vn here to call this our noise voltage. And I'm going to make a point to note that this is typically expressed in volts squared. Okay. So average power, I feel pretty strongly that most of you should be comfortable with that as a concept. We're getting a little weird here by throwing away the resistance value, but since we know that that would just be V squared over ohms, it makes kind of sense to calculate noise as a function of volts squared. We can make this average power quantity more useful if we take into consideration the frequency content of the noise, okay? So let's say that we have a group of men talking. What would we expect the frequency content of their speech to have that the frequency content of, say, a group of women talking doesn't have? Yeah, so it'll be amplified in the lower frequencies, weaker in the high frequencies, and probably the opposite would happen for women. We could actually observe that by hooking up a microphone to what's called a spectrum analyzer and literally looking at things, right? So the frequency characteristics of noise are best summarized by what's called the power spectral density. Or PSD. And in this class, we're going to give this a symbol S V as a function of F, where we're considering a noisy voltage signal. So S is power spectral density. Our subscript V is going to be for a voltage. And then F just means that this is a function of frequency. Power spectral density is defined as the average power carried by a noise Vn of t in a 1 hertz bandwidth around a frequency f. And it quantifies how much power the signal carries at each frequency. So if we were to take a noisy signal, Vn of t, pass this signal through a band pass filter, where this bandwidth is exactly 1 hertz. We'd get something like this. Oops, actually, that's wrong. B N F1 of T. So we'd wind up, since we're dealing with a brick wall filter here, we'd wind up still have it noisy, but we kind of smooth out some of the rough edges as we throw out all of our unwanted frequency. Pass this into some sort of box capable of squaring our waveform. What we would get, running out of room here, something like this. I'm going to color this in a little bit here. Where the area under this curve represents the noise power at this specific frequency of F1. And then we repeat that for all frequencies. And what we wind up getting is the power spectral density, which should look something like this. So let's call this frequency 1, frequency 2, all the way out here to some frequency n. And let's say it has this value. And now in green, I'm going to connect the dots here. This is what our power spectral density SV F graph is going to look like. And if we went upstairs to Dr. Chen's lab, Nefkin 200, and got one of his spectrum analyzers out, we'd find something that looks like this. What if we were trying to find the power spectral density? Let me ask you guys a question that you guys maybe haven't been asked since you took linear systems and signals. What would the power spectral density function of a pure sinusoidal wave look like? Yeah, a Dirac delta function just at that specific frequency, right? But as we get into other signals, we wind up decomposing it and they kind of spread out, and where the amplitude is higher, we get larger peaks, and where the amplitude is lower, we get lower peaks, and that's all that's happening. So we're just building this big spectral density function out of the Fourier transform of any signal that we have. That's exactly what this represents. So trying to tie it back to something that you guys might have some clue of what the hell I'm talking about. All right. So our power spectral density is measured in units of volts squared per hertz. Because again, it's the amount of power carried, where we're being weird and measuring power in volts squared in a 1 hertz bandwidth. All right. We can also take what I'm going to call the noise voltage spectral density. So it's not the power. So I'm going to call VN bar is going to be the square root of our power spectral density. And so it's measured in volts per root hertz. Okay. I'm introducing this because the sources that I've dealt with, which is I think 4 different textbooks and a couple of websites or whatever, kind of play fast and loose with whether they consider the power spectral density to be volt squared per, like whether they're using this or this, because they effectively represent the exact same thing, right? It's just you take the squared of one to get the other. Okay. So I just wanted to make sure that both things were introduced. So a very common type, write this down. A very common type of power spectral density is white noise. So for white noise, our power spectral density graph would look something like this. SV. Just be a flat line, okay? So white noise is characterized by the fact that it has the same noise power across all frequencies. So in practice, this can't happen. Why? It's an infinite amount of power, right? If we integrated this thing, that would be the total power generated by the noise source, which in this case would be infinitely large, which would then require an infinite transfer of energy and all those other little physics oh no's that we can't have happen, right? But in practice, we can see that over frequency bands of interest, a lot of things are going to have this simple spectral density. Resistors are one of them, okay? Until you get to a frequency of about 100 terahertz, a resistor is effectively a white noise generator in a circuit. And then after 100 terahertz, which is just shy of visible light frequencies, it finally drops off. So it creates a lot of noise in all of our systems. It's going to be one of the biggest contributors that we're going to see. Anytime we have a physical resistor, we're just adding noise to a circuit. And it's just those damn pesky random atomic vibrations that are messing everything up, okay? So one very interesting thing, and it should be kind of intuitively obvious, at least for the electrical engineers here at this point, is that if a signal with a spectral density Sx of f is applied to a linear time invariant system with a transfer function h of s, then we will see that Sy of f is simply equal to Sx of f times the transfer function of f squared, where this guy represents a linear time invariant system, or all that fancy stuff you guys talked about in 321. And I guess you would be talking about right now if you were in controls and not in this class, okay? So what that means is that the power spectral density of the input signal is shaped by the transfer function of the system. So as an example, and I might have to come up with a better example because I don't know how many of you guys had landline phones growing up because I'm getting real old. Let's say that we have a voltage signal that represents the human voice. All right. Its power spectral density as a function of frequency should look something like this. Relatively flat and then it falls off at somewhere around 20 kilohertz. Okay. Bell Labs, for whatever reason, design their telephone systems, their analog, old school landline systems, in such a way that the transfer function of these guys looks something like this. All right. Here is HF. And do this in purple. Curve too far inwards. I apologize. All right. So this guy right here, sorry, this should be 4 kilohertz. And this guy right here, I think was around 400 hertz. Effectively, even though the human voice, or at least the audio frequencies that humans can hear, is roughly 20 kilohertz, they designed their system as a bandpass filter, where everything below roughly 400 kilohertz or 400 hertz gets cut off, and everything above, it says 4 kilohertz here, but I think it's actually 4,300 hertz, also gets cut off. So if you've ever heard, and I think I talked about this way back in circuits too, but if you've ever been put on hold and they play music, it needs to be that shitty Muzak where everything falls between these ranges, because if they don't, it sounds terrible. So if you were a kid like me, and you call into a radio station or something like that where their hold music was Van Halen, it just sounded like a bunch of static and garbage because it couldn't replicate the sound of cymbals and things like that over the analog landline. Okay. So what you would wind up seeing is that the actual output waveform, the out of T, got smoothed out because a lot of its information was filtered away. And the spectral density of the input signal was also significantly shaped by the transfer function of the system, right? So the reason why I say that this should be fairly intuitively obvious is because it's the exact reason that filters exist, right? That's why we use filters to get rid of noise, is because they behave in this method. They suppress unwanted signals, okay? All right, so the next thing that I want to talk about is correlated and uncorrelated sources, all right? So when analyzing a circuit, we are often going to need to add the effects of several noise sources together. And how we do that depends on whether or not the sources are correlated or uncorrelated. How many of you guys have had stat 405? Or did you guys talk about correlation functions in math 243? whichever one you have baby statistics in. Is that 243? 242? It's been a hot minute. Okay. So correlation really just means like how similar the signals are or kind of how similar their origins are. Okay. So for example, let's say we go to I'm not a Louisiana Tech football game because no one ever shows up. Let's say we go to a Saints game. All right. Say we're going to the Superdome and it's before the game. So people are talking to their friends. There's noise being made by the vendors trying to get you to buy an $11 Michelob Ultra, all that kind of good stuff. There's a lot of general individual little noises that kind of don't have anything to do with each other. That's uncorrelated noise. Now, when the Saints score a touchdown and everybody loses their mind, that's correlated noise because it's all of the noise is being generated by the same input, okay? So what we can do to determine the noise power for multiple noise sources is we can say that the average power is going to be the limit as t approaches infinity of 1 over t times the integral from negative t over 2 to positive t over 2 of noise signal 1 plus noise signal 2, etc. And then square the sum of all of those noise voltages and then take the integral. Go ahead, right? So I'm gonna try to trip you guys up again. If we have multiple noise voltage sources, and we want to know the total power, why can't we just use a superposition theorem and say treat each noise voltage source individually? Yeah. Doesn't matter how many sources. So if you have a circuit with 35 voltage sources for whatever reason, you could use superposition to figure out what each one did. The problem here is that power isn't a linear quantity, right? Power depends on the voltage squared, not the deterministic voltage itself, right? So because we're looking for power, we cannot use superposition theorem, all right? So what's going to happen, and let's work this if there were just two noise voltages, we're going to wind up getting the limit as t approaches infinity of 1 over t integral negative t by 2 positive t by 2 vn1 squared plus the limit as t approaches infinity 1 over t integral negative t over 2 positive t over 2 vn2 squared dt. Goodness, my nose is itching. Plus the limit as t approaches infinity of 1 over t integral negative t over 2 positive t over 2 twice vn1 times vn2. So this guy right here is literally the average power of that voltage noise 1, right? So this, we could call it P average 1, representing the average power of noise voltage Vn1 by itself. This guy right here would then be P average 2, which represents the average power of that noise voltage signal Vn2. And then this guy right here is the correlation term, right? So if our noise voltage sources are uncorrelated, we're going to expect this guy to effectively go to 0. And then we could just as easily apply the superposition theorem and we'd wind up getting the right results for kind of the wrong reasons. Which is very similar to when we talked about the instantaneous power in multi-frequency circuits too. All those, when we were taking the average power, all those cross-frequency terms went away because the signals effectively aren't correlated to each other, right? That's the exact same thing happening here, okay? So P average 1 is me and my wife talking before the game. P average 2 is somebody on the other side of the stadium having a conversation. This guy right here represents what happens when the Saints score a touchdown, all right? The overwhelming majority of the noises that we will be considering, so we're going to kind of go at it from a component by component and source by source level, are going to be uncorrelated except for transistors, because of course they have to make things hard. All right. So the next thing that I want to talk about is thermal noise. All right. So thermal noise is caused by the random motion of electrons in a conductor, right? So this random motion introduces fluctuations in the voltage measured across the conductor, even if the average current flowing through the conductor is 0. Power spectral thermal noise is proportional to the absolute temperature, and it is generally considered to be white noise, right? So resistor noise falls into this case, okay? For a resistor, where thermal noise occurs because of random vibrations of atoms, we have a power spectral density, SR of F, is equal to 4 kBT multiplied by R for frequencies. So let's say 0 hertz is less than or equal to, our frequency is less than or equal to, like I said earlier, I think 100 terahertz. You may also see this given as Vn squared with a bar over it as 4 kBTR, where this is really letting you know that this power is measured in volts squared, okay? So as I mentioned earlier, this resistor, depending on its resistor value, acts as a noise generator for a circuit. So we can develop an equivalent model that's actually pretty simple, all right? So we have a noiseless resistor in series with a noise voltage generator. I'm trying to think of how I want to approach this here. So some textbooks modify this equation by multiplying this quantity by B, where B is just the bandwidth, Okay, so effectively they do that to say that the amount of noise power that's generated by an individual resistor isn't infinite. For our intents and purposes, it really doesn't matter kind of one way or the other, but having the noise power or the power spectral density doesn't really tell us a whole lot unless we know what frequency band we're looking at, right? So if we were looking at, so let's say that we have a low pass filter, okay? We have a resistor R in series with some capacitor C. Here's our input signal. And here is our output signal, right? So if we wanted to know how much the resistor contributes to the noise of this guy, what will we need to do? Okay, so we go back a couple of pages here in my notes. If you recall, the output noise, so let's call it S out, is the input noise, S in, and the magnitude of the transfer function squared, right? So in this case, our input noise is the noise that's being generated by the resistor. So we could model this as if we had turned off our input signal entirely and only put in that noise voltage generator in series with our resistor. And we want to see what noise we get at the output. Which is a pretty reasonable thing to want to know about, right? What is the transfer function for this guy? It's been a hot minute since you guys did this stuff, right? So this basic filter, we look at the top left-hand corner here, is just a voltage divider circuit for AC signals, right? So our transfer function, H of omega, I'm doing it this way because that's how I taught it back in circuits 2, would have been, sorry, let me redefine this thing here. The out of omega over Vn of omega. So that's going to look like the voltage drop over the capacitor, or actually the impedance of the capacitor, 1 over j omega c divided by R plus 1 over j omega c, which if we multiply through by j omega c over j omega c gives us 1 over j omega RC plus 1, right? So that's our transfer function as a function of angular frequency. We need the magnitude of this guy squared as a function of linear frequency. So the magnitude squared, how do I get the magnitude squared of a complex number? Because that's exactly what our transfer function is. Exactly right. Multiply it by its complex conjugate. So that's going to be 1 over j omega RC plus 1 multiplied by 1 over negative j omega RC plus 1, excuse me, gives us 1 over omega RC quantity squared plus 1. And then to go from angular frequency to linear frequency, we just need to know that omega is equal to 2 pi f, right? And so that's going to look like 1 over 2 pi f RC squared plus 1. So at our output, what did I call it? I think it just, yeah, S out, getting things mixed up, sorry. S out is going to be 4 kBT times R, which is our input noise, spectral density, multiplied by our transfer function, 2 pi f RC quantity squared plus 1 just looks like 4 kBT R divided by 2 pi f RC squared plus 1. So this is what our power spectral density for this guy looks like. So it's obviously been shaped by our transfer function. What if we wanted to figure out what the total noise power was? All right. So our total output noise power, we would integrate this quantity S out with respect to frequency. So we're just taking the area under the curve of our power spectral density, which gives us the total power. So what's interesting here is that since our power spectral density of our resistor is effectively white, we would expect this to be potentially really large. But we'll see that our filter circuit takes care of things pretty rapidly here. So let's do the math. I'm going to have 4 kBT R divided by 2 pi, actually, hold on, 2 pi RC squared F squared plus 1. I'm taking the F out of there because I'm integrating with respect to F. Let's see. You may recall that the integral of 1 over alpha x squared plus 1 dx is 1 over the square root of alpha times the arctangent of x plus c, where I'm just treating this 2 pi RC quantity squared as alpha, which gives us 4 kBT R divided by 2 pi RC times the inverse tangent of evaluated at infinity and 0, which comes out to be, so we would have, let's see, 2 kBT over pi c arctangent of f evaluated at infinity and 0, which I believe gives us just kBT over c. So the total output noise power settles down to some finite value because the capacitor, the filter forces it to, all right? What is really interesting about this, and this goes back to what I was talking about a minute ago regarding bandwidth here, is that in this network, even though it's the resistor that's generating the noise, right? The result is completely and utterly independent of the size of the resistor. Does that make sense? So let's think about what this circuit does, okay? So as the resistor value increases, what happens to the noise that the resistor generates? Goes up, right? So the value of the power spectral density should go up. What about the bandwidth of the filter? So a low pass filter, what's the cutoff frequency for a simple RC low pass filter? Any of you guys remember? Got filters in 10 different classes at this point, I think. Nobody remembers anything. It's 1 over RC. So as the resistor value goes up, the bandwidth goes down. Right? So effectively, the increase in the R here gets counteracted by the decrease in the bandwidth. So that it doesn't actually matter what the value of R is. They're always going to exactly offset each other. All right, the last thing that I want to talk about here is simple application of Norton's theorem, okay? So for this particular circuit, we represented the resistor by a volt noise source in series with a resistor, which is just a practical voltage source. So we can actually use Norton's theorem to generate one that has a noise current source instead, because sometimes that will make our lives slightly easier, right? So I have a resistor, noiseless resistor R in series with some noise voltage source, where this is 4 kBT multiplied by R. This is electrically equivalent to some noise current power spectral density 4 kBT divided by R in parallel with our noiseless resistor R. That's all I want to talk about today. We're going to get into MOSFETs and all that kind of stuff on Wednesday. And then once we learn about the noises in MOSFETs, let's talk about this pretty generally. Do you think there's going to be some thermal noise in a MOSFET? See general head shaking of yes. Why?
Because it has some like resistance, but still electrons flowing through it.
For sure, absolutely. So there's actually going to be multiple instances of thermal noise in a resistor, right? So the polysilicon gate is resistive. So it's noise. The active regions also are resistive. So they contribute noise. The channel is going to contribute a whole heck of a lot of noise because it has a lot of electrons bouncing around off of ions in there, right? But we're also going to have what's called flicker noise as well. And flicker noise is very, very frequency dependent, right? All that resistor noise is going to be effectively frequency independent, but the flicker noise is also called 1 over F noise. It has a lot to do, it's been 8 years, hold on, let me think about it. Dangling bonds. So that interface between the substrate of the silicon and the silicon dioxide, right? So you have a crystalline, highly ordered material and then directly above it is an amorphous structure. So there's going to be a lot of dangling bonds where, have you guys learned about crystal defects at all? So one of the biggest crystal defects is that they're a real thing and don't extend on into infinity, right? Because that counts as a lattice defect because the lattice stops, right? So when you have that interface between a highly structured area and an unstructured area, there's going to be a lot of dangling bonds, which are a lot of places for electrons to go hang out for a second and then go on their merry way. And that causes a heck of a lot of noise in transistors because they operate on the fact that there is a mismatch, a material mismatch between that oxide interface and that crystalline interface. So we're going to talk about all that kind of good stuff, and then we're going to talk about noise in circuits and kind of go through what I think is probably the most important topic in considering noise, which is called the input referred noise. And I say that because what we're going to see is the noise at the output of systems. But none of that really matters because we are concerned about signal to noise ratios and stuff like that. So we're going to learn techniques to refer all of the output noise to the input so that we can compare it to our signal strength. And so that gives us kind of an apples to apples comparison at all points, regardless of the type of amplifier. So I mean, it works for op amps, it works for BJT amplifiers, it works for MOSFET amplifiers, all that kind of good stuff. We can see how the noise behaves, model those sources and all that kind of good stuff. So that's where we're headed from here. All right, thank you guys.